All right, this chapter is on electric current. And when we talk about current, we're going to be talking about the movement of electrons. And really, electric current runs the whole world nowadays. The whole technological revolution is because of current. All right, so when we look at current, it's nice to use the analogy of water flowing. It actually works fairly well. We can have water flow from a high pressure area to a low pressure area, and we can have a continuous flow of water if we use a pump. And you're going to see this analogy of water used again and again when we talk about current. It just works kind of well. All right, so as we use electric current, right, we have a battery here. The battery is going to be very, very, very similar to the pump. It's going to cause the current to flow. It's going to give us our flow of electrons. Remember, we talked about a capacitor in the last PowerPoint, and I said that flow was irregular and you could have large voltage and large amperage and all that. A battery's different. It kind of magically regulates the current. It just gives out a certain amount of electrons over a certain amount of time, and it's a very steady pace, which for us is going to be a beautiful thing. All right, so let's look at our analogy over here. We have the pump. That's the battery. And this is a simple circuit. This is a circuit diagram, and it's good to have a look at this so we get used to what it looks like. In plumbing, if you have a pump and you pump it, you can have a valve. If your valve is this way, your valve is on, it's open, water flows through. And if it's across, that means your valve is closed and no water will flow through. All right, so this valve is open, we have water flowing through it. The switch here is closed. This would represent a closed switch. If you want it open so that the current flows, you actually kind of shut the door, but that opens up the wire so that the current can flow through it. Right now, you can imagine the electrons hit here and they can't go anywhere, right? They're stuck. If you want them to keep flowing, and this is the wire right here, this is the wire where they're flowing. If you want them to keep flowing, you better shut that door so that they can flow along it. So that's a switch, just like a light switch. All right, a resistor. Well, a resistor over here is anything that would reduce the flow of water. If you get a small pipe, if you get a clog in your line, anything that would kind of slow down that flow of water. And so here it's represented by a hose that would be a smaller diameter than the regular pipe. Over here, we represent a resistor is just an up-down line, and it's something that's going to slow down our flow of electrons, all right? And then we complete the circuit. It comes back and around. So what this might actually be is a battery to an on-off light switch. The resistor here is a light bulb. Light bulbs are a special kind of resistor. They heat up and then give off light, but they do resist electron flow, which is why they heat up and give off light. All right, so what an ammeter is it just measures the current in your circuit. So you can put an ammeter in and it will measure the current on wherever you stick it. Pretty simple. Voltage sources. So you can do different things for voltage sources. This would be a battery, basically. This is a chemical battery. You can have a simple mechanical generator, which is going to be magnets and a coiled wire to create a current. Either way, you just get a push of electrons, essentially, that are going to flow. All right, so a chemical battery, this is supposed to be grayed out. I don't think you need to write this, my apologies. A chemical battery is, fortunately for us, chemistry and not physics, but we're just going to take a quick look at it so you have a basic understanding of what's going on. You can have two different sides, right? You're going to have your zinc side and copper, and you dip them into an acid bath. And here I want you to think this is why, batteries can be dangerous. But on this side, it happens that the acid removes some of the positive charges from the zinc, and they end up in solution. So the current can actually flow through this liquid. This is now a ionic solution. So it's a complete circuit. If you look at it and you think, well, the electrons just flow and they stop here and they can't go across, that's not correct, because we can actually flow through a liquid if it has ions. So now we have some ions, and on this side we have extra electrons, and on this side from the copper we have extra protons. The electrons have been removed into solution, and so you will actually generate a current from that. All right, so rechargeable batteries, and again, my apologies, this was supposed to be in gray. Rechargeable batteries are, what the idea is here is you have the same thing that we saw on the previous slide. You have some source of acid here. You have a little lead oxide and lead metal. And so you're going to have your electron flow this direction when you go to start the car. You use up the battery. You have to have a strong battery start the car, right? That's what the battery's sitting there for. Then while the engine's running, what it does is it actually reverses that flow and recharges these, right? So you can do that over and over again. Eventually it stops working, but reversing the flow of electrons will actually recharge these. And that's, again, a chemical equation going on in here, and the physics of the electron flow is what's going on up here. Okay, electrical resistance. When we talked about electrical resistance, remember I said with the water it was like having a thinner hose, like a fireman's hose, really thick, will have less resistance in plumbing, and a small hose you'll have more resistance. Well, same idea for electricity. If you want a lot of, easy flow, you're going to have wider wires. Now, the disadvantage is copper's really expensive, so you don't have really wide wires just going everywhere. We do encounter electrical resistance in our circuitry everywhere. You encounter it because, there's a trade-off there. You can't just use super thick wire everywhere. But for example, in your jumper cables where you really want to minimize electric resistance and you don't have to go a really long distance, it's a great idea. They tend to be very thick and well insulated, and again, be careful. All right, Ohm's law. In Ohm's law, we just take current, and current is the flow of electricity, right? And we take voltage, and voltage is, the way I tend to think about voltage is, like if you have a rock that's going to fall off of a small cliff, it has a certain amount of energy. And a rock that falls off of a really tall cliff, same exact rock, has more energy. Well, that's kind of how voltage works. It's the amount of energy. So you have, your electrons, and it's how much push they have. Are they going to fall off of a small cliff, or are they going to fall off of a large cliff? And that's how you can think about your voltage. And then you have resistance, how much resistance it is. And typically, current is given in amps. Ampere is the guy, amps is the unit, and I think in the SI system it's just an A for amps, but you're going to see almost everywhere it's actually written AMP, so either way we'll say is correct or usable. Volts is simply V, and then ohms, which is the unit of resistance. How much resistance is there to the flow of electrons? How much resistance? It's almost like how much friction do they encounter? And then you can see the symbol for ohms there. All right, so resistance of water. If we had pure water, pretty high resistance. This is why people usually don't get electrocuted, say in Lake Tahoe, which is pretty pure water. Problem is, most water has ions in it. It's not deionized water like we use in the lab. Even Tahoe's not. So most water has ions, and you can get electrically shocked in most water, like even in your bathtub. That's why you're not supposed to blow dry your hair while you're sitting in the bathtub. But certainly if we add salt to a water, we've greatly increased the ion concentration. and we've lowered the resistance. All right, this is all grayed out. You don't have to write it, but it's just kind of interesting. Our nervous system uses the exact same idea as electric currents to the point where you can actually, shock the nerves on this is a dead frog in case you didn't catch that. And the frog's leg will jump as if it were having a nerve impulse. Oh, this is all supposed to be gray too. My apologies. So electrical current in the heart is actually what causes it to beat. Okay, here's electric shock. And you'll notice that the chart on electric shock is not given to you in volts. Even though you have all those signs that say danger, high voltage, blah, blah, blah. Voltage is how far that can jump in air. Like a higher voltage thing can jump through the air farther. So the danger is, when you get close to it, it can jump to you. The volts don't actually kill you. It's the amps that kill you. How many electrons, just the sheer number of electrons, not how far they jump. So you can put a couple thousand volts on a balloon, you can shock somebody, and when it jumps through the air, you can be in the thousands of volts, and they're not dead because it's got just the tiniest bit of electrons, very small amps. So when you go around and you rub your wool socks on the carpet and you go up and you shock somebody, you're looking at 0.001 or about there amps, and you can feel that. If you get to 0.005, it's painful, okay? And then if you've ever shocked yourself fairly well, you can actually get involuntary muscle spasms. This is painful and getting toward dangerous here. At 0.015, you get loss of muscle control. And then at 0.07, this can be fatal if you hit your heart at the right time in its heartbeat and if it lasts for more than a second. All right. Now look off to the left, which is grayed out. But when your skin is dry, the ohms, the resistance it says 100,000. It can actually, if your skin's really dry, it can actually be even higher. But when your skin is wet and salty, the resistance drops greatly, all right? And the way to think of this is you walk around holding one of those 9-volt batteries, and both the positive and negative terminals are right in your hand, and you never really feel anything because your hand's fairly dry, the resistance is pretty high, okay? But you can take that same 9-volt battery and stick it onto your tongue, which is wet and salty, and all of a sudden you can feel that. All right, so if your resistance is 100,000 ohms and you have a current pass through you that's 120 volts, what is a current passing you, when you have the 120 volts? So you need to find the current when you have the volts and the resistance, and that was that formula above, and then do it again if you have your dry skin. And you will see mathematically why that's true. All right. There's two different kinds of currents. One's called direct current and one's called alternating current. And direct current is a battery. So when you have a battery, you literally have electrons that will flow from one end to the other end directly. All right. They just flow. They just flow in one direction. You run out of electrons, you run out of battery. All right. Alternating current is what you have in your sockets. And they have a wave here showing alternating current. But what's actually happening with your electron, so here's your direct current. And if you can imagine the electron's just moving like this, and it actually flows from one area and eventually comes out the pipe somewhere else. All right, over here, what's actually happening to each individual electron is it's just going back and forth. It's just going back and forth. It's a pull and a shove and a pull and a shove and a pull and a shove. And that pull and shove is enough to give us power to run stuff. The electrons never actually go anywhere. They're actually just oscillating back and forth. Another way to think about this is PG&E is so cheap they don't even give you electrons. All they do is take the electrons you already have and move them back and forth like this. And that is your alternating current. It's just an electron that oscillates back and forth. All right, so your direct current is battery, like I said, very, very classic. Battery is a great example. All the power supply here is going to actually be AC. And it does make sense because you're trying to transmit electricity long distance. You really can't just send electrons one way. All right, so let's look at how electrons actually move around in a conductor. It's actually amazingly slow, even though they travel very, very fast, but they travel in a random direction. So the solid line is supposed to be here, an electron just kind of bouncing around, hitting atoms, and it would randomly stay in this area forever, okay? It would just kind of, no net movement in any one direction as it bounced around, all right? We apply a voltage to this and it's just going to it's still going to bounce around. It's actually, even if the voltage is ultimately taking it towards the right, you notice it only shifts it a little to the right. Kind of think like at a snail's pace this would occur. So with direct current, we're just going to, this one's just going to kind of, keep bouncing around, and eventually the net movement will be that it moves to the right. Alternating current, what's going to happen is that these and a bunch of electrons together will just kind of bounce around, but they'll ultimately move to the left, and then they're going to bounce around and ultimately move to the right, and then they're going to go back to the left and then back to the right. All right, so the electrons in DC do move. They move slowly, and they still have that randomized motion inside of your conductor. Okay. So we can actually have the resistance go down if you supercool something. And the reason is there's less of this random bumping into the atoms. So you get more of the direction you want. So you'll see in the diagram here, those electrons, were kind of spastic when they're warm. They're down here, they're over here, they're over here, they're over here, and your net ends up just being, if you have voltage, the net ends up shifting over a little bit. Well, if you super cool them, they kind of chill out. They don't do all this random bouncing around, and they respond better to the voltage, getting them to go in one direction. They still don't just all line up and, go straight, but you do get a better result. All right, ohmic heating is why light bulbs work, actually, the regular incandescent light bulb. And when something flows through something that resists the flow, you can get heating. And in fact, a light bulb will keep, someone's cellar on the East Coast can stay warm with one single light bulb. And that is from the filament literally just heating up. Okay, that is how your rear window defoggers work. We put a current through them, and they're just a wire with a good amount of resistance in them, not enough that they light up. We don't need these to start to glow, but enough that they heat up, and the right material that it heats up, and then it defogs your windows. All right, cooking, you can do this with hot dogs, and remember, it'll work with hot dogs because they have salt in them, and we can actually get a current to run through them. It does kind of look like a fun lab, I have to admit that. Okay, power. When we talk about electric power, now we're getting into watts, and everyone has heard watts or kilowatts, or you look on a bulb and you know that it's a 100-watt light bulb. And what a watt is the voltage times the current. It's how much energy, how much of a drop off each electron has, times how many electrons there are, the current itself. How many of these electrons do you have flowing? And that'll give you your total power. Okay, and that power is in watts. All right, so you can do a little fun math there. A kilowatt is 1,000 watts. We know that because a kilo anything is 1,000, all right? And then a kilowatt hour is going to be how long? So if you leave something that is 1,000 watts on for 1 hour, you've just done 1 kilowatt hour, right? So you actually look on your appliances and you can see ratings on them at how energy efficient they are. And it's always going to be in your kilowatt hours. Like, how efficient is it if you leave it on all day? All right, so when we look at circuits, we're going to look at two kinds of circuits. One's going to be called parallel, and one's going to be called series. And they're going to be quite different. So we're going to just take a look over here, and I want you to notice that in each three of these drawings, each bulb is directly, essentially, gets its own unique voltage across it because it's attached to this battery. Whether it flows from here, or in this case, it flows to here for the first light bulb, and it flows to here for the second light bulb, and the flow would be from here to here for the third light bulb, meaning it could flow to that light bulb without having to go through any other light bulb. It can get there. There's a path to each of these light bulbs without it first having to go through a light bulb, which is going to be different than in series. So just remember that. Right now I'm only showing you parallel. Here again, you can get to this one, you can get to the second one, and you can get to the third one without going through any of the other two. So these are all three different forms of a parallel circuit. All right, now we have a series circuit. All right, so take a look at this, and there's no way for that electricity to get through, right? It has to go through this one to get to here, to get to here. And what that means is as it flows, the first bulb gets all the sort of the fun voltage, right? It gets to be nice and bright. But then this guy just gets second helpings, right? He's not getting as much as the first guy. And the third guy, he's practically getting any electricity at all. And believe it or not, houses used to be wired in series. So you would, turn on your vacuum cleaner and all of your lights would dim. And if you're living in a house right now where you turn on your vacuum cleaner and all of your lights dim, it's because it's still probably run in series. They stopped doing that sometime in the 60s, I think. So anyway, so that's a series circuit. All right. Then we have a parallel circuit, which was the one I already showed you. And again, in parallel, you can see that each light bulb gets its own unique, gets its own electricity without it going through the other three. Now, so they're all just equally as bright, right? They're all equally bright, except for the poor guy who has his switch open. The downside of this, then, though, is you're using 3 times the electricity from your battery. So there's always a payoff. There's no free lunch here. This isn't magic. In the first one, the series one, if we're using 1 time, say just 1 times the electricity. In this one, we're going to be using 3 times that because we got 3 bulbs in parallel. All right, so let's take a look at this one. This one's interesting because we have A and B, right? A and B, and they are for each other. They are in series to each other. But they are in parallel to C. So let's imagine we cross out A and we turn off A. A is not on. Now B and C are simply a parallel circuit, and we know that B will be equally bright as C. Right? They're going to be equally bright. But when we turn A back on, these are going to end up being about half as bright as C. And the reason is they have to split their electricity, and depending on which way it goes, one's going to end up being slightly brighter than the other. Okay, so remember I said there's no free lunch. So houses used to be run in series, and if you turned on the vacuum and the lights and the toaster and everything else, everything just didn't work quite as well, right? Your vacuum didn't suck as much and your lights were dim, but there wasn't really a danger of overloading it. When we put it in parallel, now everything works just as well, but it's drawing a ton of current. And so to protect the houses, you put in something called a fuse. And what a fuse does is you just put in a fuse, and what a fuse does is essentially it'll overheat and it'll melt. And that'll save everything else. It'll save your house from catching on fire. It'll be a wire that's made of, a softer metal, something that when it gets hot will melt, and when it melts, it's going to stop. It's no longer going to be connected from end to end, and the current will stop flowing, and that will save your house. All right, so your fuse is designed to melt, which is great, but then it's melted, and do you have another one, and do you run to the store to go get a fuse? Well, there's an even better idea, something called a circuit breaker. We tend to kind of use these interchangeably because we'll say, run to the fuse box and flip the switch. It's a circuit breaker, but same idea. So in this case, when it overheats, it just pops the switch. And so you just run out to your fuse box, and what we call a fuse box, it's a circuit breaker, and you flip it, and then the current can run through it. And again, that protects the houses that are now run in parallel and can draw too much current if you turn everything on. Okay, just for fun.